up till now, we've talked primarily about first-order differential equations and how to solve them. Now, if you remember, back towards the beginning of the course, we talked about the fact that there could be higher-order differential equations, and you practiced figuring out what the order of a differential equation was. Now that we've talked about the ways to solve the first-order differential equations, we're going to take some time to explore how we can solve higher-order differential equations. That is, differential equations that have a derivative raised to a power greater than 1. The first type of higher-order differential equation we're going to talk about are linear equations. Now, as with first-order differential equations, we can solve a differential equation itself and come up with a general solution. And that general solution is some family of solutions that's defined on some interval. So we're able to do that with higher order differential equations. However, sometimes we want a particular solution. And again, as with first order differential equations, if we want a particular solution, we need additional information. That additional information comes in the form of either initial conditions or initial values or boundary values. So let's first talk about initial value problems. An nth order initial value problem, or IVP, looks like a differential equation where we have some function of x, we'll call it a sub n of x, times the nth derivative of y with respect to x, plus some other function, maybe the same function or a different one, a sub n minus 1 of x, times the n minus first derivative of y with respect to x. And we keep doing that, moving down our chain of derivatives until we have a sub 1 of x times our first derivative of y with respect to x, plus a sub 0 of x times y. And that's going to equal some function of x g of x. And that is a higher order differential equation. Now, in order to be an initial value problem, we need to set that differential equation subject to some initial conditions, or ICs. So, if we have an nth order initial value problem, we need n initial conditions. So, those initial conditions will look like our initial value of x, x naught. If we take y of x naught, then we get an initial value of y, y naught. If we take the derivative of y at x naught, that's going to give us some initial value of the derivative at x naught, which we'll call y1. And we continue doing that, taking higher and higher derivatives until we're taking the n minus first derivative of y, and we're evaluating it at x naught, and finding an initial y value or an initial derivative value there we'll call y sub n minus 1. Now again, just like in our first order case, these differential equations, these initial value problems, they may or may not have a solution, and it may or may not be unique. So we have a theorem about the existence of a unique solution to help us determine when there is a unique solution. So if we take all of those coefficient functions of x, a sub n of x, a sub n minus 1 of x, down to a1 of x and a naught of x, and our function of x that's on the right-hand side of our equal sign, g of x, if they're all continuous on some interval I, and we let a sub n of x not be 0 for every x in the interval, then if x equals x naught, so our initial value of x is some point in the interval, then a solution, y of x, of the initial value problem that we talked about as our nth order initial value problem exists on the interval and is unique. The other way that we can get a particular solution when we have a differential equation that's a second order differential equation is we can have boundary conditions given to us. When this happens, we're dealing with what's called a boundary value problem, or a BVP. So these differential equations look something like solve a2 of x times the second derivative of y with respect to x plus a1 of x times the first derivative of y with respect to x plus a0 of x times y equals g of x. And again, that would give us a family of solutions to this second order differential equation. It would give us the general solution, and in order to make it a boundary value problem, it needs to be subject to boundary conditions, or BCs. And since it's a second order differential equation, we'll need two boundary conditions to find a particular solution. Since it's a boundary value problem, these will look like using a as some x value. So we'll know y of a equals y naught. And then some other x value, b, will give us y of b is y1. Now a and b are looked at like as the ends of an interval. And that's why it's considered boundaries of that interval and a boundary value problem. Now, because it's a second order differential equation, these can also come in the form of values of the first derivatives at these points. So we have actually 4 different possibilities of what these boundary conditions could look like. The most common, the first one we talked about, was y of a and y of b, knowing what those are. Other possibilities are that we know the first derivative of y at a is y naught, and we know that y of b is y1. Or instead we might know y of a is y naught, and the first derivative of y at b is y1. Or we might know the first derivative at both of those points, a and b, and we would use those values, y naught and y1, as our boundary conditions. So let's take a look at an example that will show us situations where we might have many solutions, or just one solution, or no solution to a given boundary value problem. So let's consider the differential equation x double prime plus 16x equals 0. Now, the general solution to this is x equals c1, some constant, times cosine of 4t, plus c2, another constant, times sine of 4t. Now, to actually get from the differential equation to the general solution, we'll be talking about that as we move forward. But for right now, let's use this differential equation and consider some different boundary conditions for this differential equation to go with this, so we can figure out a particular solution from the general solution. So first, let's consider if we were given the boundary conditions x of 0 equals 0 and x of pi divided by 2 equals 0. So now we can use these to solve for our two constants. So let's plug in the first one first. So we'll put 0 in for t and 0 in for x. In doing so, I'll get 0 equals c1 cosine of 4 times 0 plus c2 sine of 4 times 0. So multiplying 4 times 0 is obviously 0, which leaves me with 0 equals c1 cosine of 0 plus c2 sine of 0. Sine of 0 is 0, and cosine of 0 is 1, which leaves me with 0 equals c1 plus 0, or just 0 equals c1. Now that I know that c1 must be 0 to satisfy my first boundary condition, I can plug it in before using my second boundary condition. When I do so, plugging 0 in for c1, I'll get x equals c2 sine of 4t. Now I can plug in my second boundary condition to solve for c2. So I'll plug in pi over 2 for t and 0 for x. 0 equals c2 sine of 4 times pi over 2. Now 4 times pi over 2 is going to equal 2 pi. So that gives me 0 equals c2 sine of 2 pi. Now sine of 2 pi is going to be equal to 0. So that tells me that I have 0 equals C2 times 0, or just 0 equals 0. And what this tells me is that no matter what I choose for C2, this boundary condition is going to be satisfied. Therefore, as long as C1 is 0, then I can have many solutions, in fact, infinitely many solutions. Now, to write what those infinitely many solutions look like, I need to plug in 0 for C1 because that actually has to be 0. But C2 was free to be anything. So I'll plug in 0 for C1, so I'll end up with a solution of x equals C2 times sine of 4t. And since, again, C2 can be anything, there are infinitely many solutions when we have boundary conditions of x0 equals 0 and x of pi over 2 equals 0. Now let's instead consider if we were given the boundary conditions x of 0 equals 0 again, but now x of pi over 8 equals 0. We follow the same process, so by plugging in 0, 0, so 0 for x and 0 for t, I know that I'm going to find that C1 needs to be 0, as I did in my first example. So we'll have C1 equals 0. Now knowing that C1 is going to be 0, I can plug that in, and then I'll use my second boundary condition. So plugging in C1 equals 0 gives me again x equals C2 sine of 4t to work with. So I'll plug in pi over 8 for t and 0 for x. So I have 0 C2 times sine of 4 times pi over 8. Now 4 times pi over 8 is pi over 2, so I'll have 0 equals C2 sine of pi over 2. Now sine of pi over 2 is 1, so that gives me 0 equals C2 times 1, or just 0 equals C2. Now, plugging in C1 equals 0 and C2 equals 0 into my general solution, I find that I have x equals 0 plus 0, or just 0. So x equals 0 is a solution of our boundary value problem, and it is in fact the only solution. Now let's consider one last pair of boundary conditions. This one being x of 0 equals 0 and x of pi over 2 equals 1. So again, when we plug in 0, 0, we know that we're going to find that C1 equals 0. And we know that when we substitute 0 in for C1, we'll have x equals C2 sine of 4t remaining. So now all that's left to do is to plug in my second boundary condition. So I'll put pi over 2 in for t and 1 for x. And this will give me 1 equals C2 sine of 4 times pi over 2. Now 4 times pi over 2 is 2 pi. So 1 equals C2 times sine of 2 pi. Sine of 2 pi is 0, so this tells me that 1 equals C2 times 0, or 1 equals 0. Now 1 equals 0 can't possibly be true, so there is no solution to this boundary value problem. So we just say no solution. So those are the three possible outcomes when you go to solve a boundary value problem once you've found the general solution.